Welcome to this Expert Explainer. As a licensed structural engineer, I'm here to tutor you step by step through a classic and honestly somewhat notorious NCEES SE vertical breadth exam problem. If you're prepping for the SE exam, you already know snowdrift problems are practically guaranteed to show up. They test not just your math, but your reading comprehension and your ability to navigate the code under pressure. Today, we're zeroing in on a leeward snowdrift scenario. So grab your calculators, because we're going to break this down so thoroughly you'll actually be hoping to see this exact question on exam day.
Here's our quick agenda for today. We'll start with the leeward drift problem, move into ASE 716 design parameters, walk through a step-by-step math breakdown, navigate how to avoid the total load trap, and finish up with our final answer and next steps.
Okay, Section 1, the leeward drift problem. Let's put ourselves right there in the exam room and look at the exact problem statement you need to solve.
All right, picture this scenario. We've got a stepped building. There's an upper flat roof with a 100-foot fetch length. The wind is blowing parallel to this fetch, picking up snow, carrying it off the edge, and just dumping it down onto a lower flat roof sitting 15 feet below. Crucially, there are no parapets or obstructions up there to catch the snow before it falls. Now, our goal here, and you should absolutely underline this word in your mind, is to calculate the maximum intensity of the leeward snowdrift surcharge on the lower roof. Your options are 35, 53, 83, or 118 pounds per square foot.
Moving to Section 2, ASCE 7-16 design parameters. Before we even think about crunching numbers, we have to establish our governing design code and pull our given parameters.
Look at how cleanly we can organize these foundational inputs. This level of organization is absolutely critical, guys, because throwing numbers around blindly is exactly how candidates fail the breadth section. The problem explicitly specifies ASCE 716 is our code. We're handed a pretty hefty ground snow load, our PG, of 50 PSF. And thankfully, to keep the math from getting too wild, our exposure factor, CE, our thermal factor, CT, and our snow importance factor, IS, are all given simply as 1.0. Getting these neatly tabulated is essentially step 0. Right, on to Section 3, step-by-step math breakdown. Let's move into the primary analysis and unveil this math sequentially so we don't get overwhelmed. Listen closely, everyone. This right here is your golden roadmap. We're doing this in 5 steps. This is exactly why we must calculate the flat roof snow load and the snow density first. They're the required foundational puzzle pieces to find our theoretical drift height. Way before we can ever calculate the final surcharge, you just can't skip straight to the end. You've got to respect the sequence.
Okay, step 1 is figuring out the flat roof snow load, or PF. We flip to ASE 7-16 equation 7.3-1. The formula is 0.7 times our 3 factors, CE, CT, and ISS, multiplied by the ground snow load, PG. Plugging in our factor values of 1.0 and that 50 PSF ground snow load yields a flat roof snow load of 35 PSF. Think of that as your baseline snow, just sitting calmly on the flat surface, totally unaffected by wind drifts. Make a mental note of that 35 PSF. We're going to need it later.
Next up is Step 2, calculating the snow density, or gamma. Basically, how heavy is this snow? Equation 7.71 tells us density equals 0.13 times the ground snow load plus 14. We drop in our 50 PSF ground snow, multiply by 0.13 to get 6.5, and add 14. Bam! That gives us a snow density of 20.5 pounds per cubic foot. Now, put on your engineer hat and do a quick sanity check. The code caps this density at 30 PCF. 20.5 is clearly less than 30, so we're good to keep going.
Time for the heavy lifting. Step 3, calculating the leeward drift height, or HD. Since this is a leeward drift, the wind is sweeping across that upper roof and pushing the snow right over the edge. So our fetch length, LU, is simply the 100-foot length of the upper roof. Using equation 7.6-1, the formula is 0.43 times the cubed root of the fetch length times the 4th root of the ground snow load plus 10 minus 1.5. Kind of messy, right? Let's substitute our 100-foot fetch and our 50 PSF ground snow. The cubed root of 100 is about 4.642. The 4th root of 60 is roughly 2.783. Multiply all that out, you get 5.55, subtract the 1.5, and we arrive at a theoretical drift height of 4.05 feet.
Step 4 is our geometry check. This is where the math meets physical reality. The crucial thing here is comparing our 4.05-foot theoretical drift to the actual 15-foot physical drop between the roofs, our clear step height, h sub c.
Imagine that lower roof filling up with snow. Could a 4-foot pile physically fit in a 15-foot space? Oh, absolutely. Because our calculated drift is much smaller than the clear step height, it's not truncated by the geometry of the building. That means we get to use the full 4.05-foot drift height for our final load calculation.
Finally, Step 5, finding the maximum drift surcharge intensity, PD. The absolute maximum intensity happens right at that vertical separation, the wall of the upper roof where the snow pile is deepest. To find a pressure, you just multiply a height by a density. So multiplying our full 4.05-foot drift height by our calculated snow density of 20.5 PCF gives us our maximum surcharge intensity right at the wall, exactly 83.0 PSF.
Section 4. Avoid the total load trap. We've got our number, but wait, freeze. Put your pencils down. Before you rush to circle an answer on your exam, I need to raise a massive red flag.
NCEES loves to use semantic traps to catch test takers off guard, so don't fall for this one. Look really closely at the options. Option D deliberately tempts you with 118 PSF. Now, where does that number come from? It's the total load. If you took our 83 PSF drift surcharge and added the 35 PSF flat roof snow load sitting directly beneath it, you'd get exactly 118. But remember that word I asked you to underline earlier? The question specifically asked for the surcharge load alone. The surcharge is just the extra load added on top of the flat roof snow load, and that is only 83 PSF. Option D is literally a trap for candidates who read too fast.
Section 5, Final Answer and Next Steps. This whole problem brilliantly illustrates how following a strict, step-by-step code methodology while keeping a hawk's eye on the wording guarantees you the points. You did the math perfectly, you dodged the trap, and therefore option C, 83 PSF, is definitively our correct answer for the maximum leeward drift surcharge. Passing the SE exam isn't just about memorizing formulas, right? It's about executing them flawlessly under pressure and seeing right through the examiner's tricks. If you want access to more questions and expert breakdowns exactly like this one, what's your next step? I highly recommend picking up the book PE Structural SE Practice Exam Questions from School of SE. It's completely packed with scenarios just like this to help bulletproof your exam strategy. As you keep studying, I'll leave you with this to chew on. Next time you walk past a stepped building in your hometown, ask yourself, what invisible loads and code traps are hiding right there in plain sight, waiting to bring it down? Keep at it, keep trusting the code, and I'll see you in the next explainer.